Hello and welcome to the session. Principles of Computer Systems LO1. Understand the architecture and key components of computer systems. How do computer systems work at their core? This video explores the architecture and key components of computer systems. From the central processing unit to memory and input-output devices, discover how they all interact. Computer architecture refers to the design and structure of a computer system. It explains how components interact to process data. Most systems use the von Neumann architecture. This design allows the processor to fetch instructions and data from the same memory. It processes them and returns results for storage or output. At the heart of the computer system is the CPU. It executes instructions and controls operations. The CPU consists of the control unit, arithmetic logic unit, and registers. The control unit manages data flow between components. The arithmetic logic unit performs calculations and logical operations. Memory stores data and instructions needed by the CPU. It is divided into primary memory and secondary storage. RAM is volatile and stores programs in use. ROM is non-volatile and stores essential startup instructions. Secondary storage retains data even when powered off. Input devices allow data entry into the system. Examples include keyboards, mice, and scanners. Output devices present data to users, like monitors and printers. They enable interaction between the user and the computer. These devices make the system usable. The system bus connects all components. It transfers data, instructions, and control signals. The data bus carries data, the address bus identifies memory locations, and the control bus coordinates actions. Together, they ensure efficient communication. This prevents conflicts and maintains system stability. The CPU is the main processing unit. The ALU performs arithmetic and logical operations. The FPU handles complex numerical calculations. Memory stores data required by the CPU. Buses connect internal components for data transfer. Data processing is controlled and timed for predictability. Clock-driven operations and structured data transfer mechanisms are used. The system clock synchronizes operations with clock cycles. State machines model processor behavior. This ensures correct operation order and data stability. The system clock generates electrical pulses called clock cycles. Each cycle has rising and falling edges. Operations are synchronized with these edges. Higher clock speeds allow more instructions per second. However, they increase power consumption and heat output. Data processing follows the fetch-decode-execute cycle. The CPU retrieves an instruction in the fetch stage. The control unit decodes the instruction next. The ALU or FPU executes the instruction. This cycle ensures controlled and predictable program execution. Data is transferred using buses between the CPU, memory, and devices. The address bus identifies memory locations. The data bus carries actual data. The control bus carries signals for read and write operations. Together, they enable structured communication. Parallel processing executes multiple operations simultaneously. It increases throughput and execution speed. Pipelining overlaps instruction processing stages. It keeps the processor busy and efficient. Both techniques enhance performance but introduce complexity. Software must be designed for parallel execution. Tasks are divided into independent units. Shared resources must be managed carefully. Issues like race conditions and deadlocks are challenges. Proper software design maximizes performance improvements. System performance improves with coordinated component interaction. The CPU works with memory to reduce data access delays. Fast registers and cache memory help. High bandwidth buses reduce bottlenecks. Specialized processors offload tasks from the CPU. Parallel processing reduces execution time. It improves throughput by handling multiple tasks simultaneously. Hardware resources are utilized effectively. However, software design complexity increases. Not all tasks benefit equally from parallel processing. Parallel processing's impact depends on software design. Task synchronization and data dependency are challenges. Some tasks must run sequentially. Coordination overhead can reduce gains. Proper alignment of hardware and software is crucial. In conclusion, understanding the architecture and key components of computer systems is essential for comprehending how systems operate and interact. Components such as the central processing unit, memory, storage, input, and output devices work together within a structured architecture to process data efficiently. Understanding how these components function and communicate supports effective system use, troubleshooting, and optimization. This knowledge provides a strong foundation for further study and practical work in computing and information technology. Thank you for watching this video. If you have any questions, please feel free to contact us via email or WhatsApp at 07484361688.